I think it's streaming now. It's just not. Well, I guess it works. Let me open YouTube for a moment. I need to change the. Okay, it seems like it's working. Okay, does the sound work? Hmm. Well, I'm just going to hope that it's yeah, seems like it's working. So anyway, going back to the actual paper. So this paper is called through a steerable lens, magnifying neural network with probability via phase-based extrapolation. Okay, what's this about? I guess I'll just start by reading after. Understanding the internal representations and decision mechanisms of deep neural networks remain critical open challenge. While existing interpretability methods often identify someone left, influential input regions, they might not elucidate how a model distinguishes between classes of or what specific changes will transition an input from one category to another. Yeah, that makes sense. So there is these limitations. We propose a novel framework that visualizes the implicit path. I was thinking that some people were believing. Bringing path between classes by treating the network gradient as a form of infinitesimal notation. Okay, so this is the like the typical kind of path interpretability methods that people use that aren't really Mech Interp, where they do things like taking the gradient of some input and seeing in some vague sense which paths matter for some output, which is not has a lot of problems because yeah, obviously most time it's just some meaningless nonsense thing, and it doesn't actually. But so this one's some kind of more interesting version of this. Okay, drawing inspiration from phase-based motion magnification. I don't know what that is. We first decompose images using invertible transforms, specifically the complex steerable pyramid. I have no idea what that is either, but I hope they explain this later. And I mean, maybe we won't be able to understand it. Like, maybe this is the kind of paper that we will actually need to spend more time actually reading beforehand or something. But I just wanted to pick something to have this week and we can try, I guess. Rather, if someone knows more about any of this, feel free to speak. Okay. Rather than iteratively integrating the gradient to trace the full path, we amplify the one-step gradient to the input and perform a linear extrapolation to explore how the model moves from the source to the target class. Someone is entering and leaving. Okay. By operating the steerable parameter, this amplified gradients produce semantically meaningful, especially coherent morphs that highlight the classifier's more sensitive directions, giving insight into the geometry of its decision boundaries. experiments on both synthetic and real-world data demonstrates that Opage's focuses per interpolation just predatory aligned semantically meaningful transformations. So fair, no interpretable lens into the neural classified interpretation. Okay, that sounds vaguely interesting, but I barely understood most of what this means. But seems like a lot of it is jargon, and they might just explain it later. Like I still also don't get what they mean by path between classes. Yeah, as a form in the infinitesimal motion. We'll see. Okay, so typical. This is the typical thing about how neural networks are very cool and interesting. And please accept our paper. Core challenges is how model interpret. Yeah, this is the excuse to cite everything. Yeah, certainty maps is typical thing people do that is not very interesting. Often lack spatial coherency. And don't know how those changing features affect classification outcomes. I mean, don't they actually just show which ones change? I guess maybe they do it by like some if they decrease some class or something. Yeah, I don't know what I mean there. Adversarial perturbation explore model sensitivity by finding minimal input modifications that alter predictions. Yes, so perturbations are typically imperceptible and semantic and informative. I mean, that's kind of adversarial. The point with adversarial examples often is trying to find the smallest change that changes the prediction. What do you want to say something? Anyway, I'll keep reading, I guess. In this work, we propose a completely interpretability, rather than highlighting input importance will preserve the trajectory that a model implicitly perceives within one class and another. Yeah, what does this mean? Okay. Inspired by phase-based model modification. Okay. I don't know what that's another paper. When implicitly small temporal displacements in a video are amplified to produce visible.
Screen share is broken. I'm looking at the YouTube live stream as well, and I can't see it, and I can't see it here on independently. All I hear is
let me try. And now?
Okay. Now let me check. I can see it now. Let's check. I'm gonna check on the YouTube too.
I think it might not be working on the YouTube. Yeah.
Yeah, it's not working there, but I can now see it.
Yeah, I can. The YouTube thing is not it's not working very well. I can't. Like, it's dying, the machine I have it on for some reason, so it's not. I can't really interact with it right now, so I just leave it there. Hope
you're recording is like
it's recording my voice at least. Yeah, I mean, people can just go look at the paper anyway. I'm not going to be. Anyway, you can see my screen at least on Discord, right?
Yeah, now I can see your screen. Yeah, at least here.
Okay. Well, people on the video that watching the video can just go open the paper or whatever. Anyway, where was it? Yeah, So yeah, basically, I still don't understand what they are doing exactly, but I guess we can keep going and maybe they'll explain it better. Anyway, we draw conceptual parallel to motion magnification. The gradient of a neural network with respect to an input image is analogous to subtle motion. An infinitesimal perturbation that matches the images to a particular target class. Yeah, I don't not sure I understand this motion magnification thing anyway. So there, and analogy is not very helpful, but okay. Due to its infinitesimal nature, this gradient is typically not visually discernible. However, by analogy to subtle motions in video that can be reversed through temporal magnification techniques, we hypothesize that it's possible to amplify these gradients in a way that makes them perceptually meaningful. Okay, so they have this thing that is used for this video thing I don't really understand. Yeah. And they want.
I'm just a little. Yeah, I also find it confusing how they went from like talking about enhancing the gradients to enhancing temporal gradients.
Yeah, they talk about this video thing, and it's apparently they are doing some analogous thing that to that on the with the gradient. I think probably if you actually understand the video thing beforehand, maybe this is a good explanation, but I don't know, maybe they'll explain more later, I guess. Like the paper is not that long.
It's
okay, so hence we treat the classifier's gradient as latent, structurally meaningful sign as a latent, structurally meaningful signal that becomes interpretable when magnified along semantically aligned axes in structural domain. Okay. To realize this, we move beyond raw pixel space and operate with a transform domain that encodes spatially localized, multi-scale, and orientation selective features. Right, so okay, so they have the gradient and 1 million round pixel space and operates within a transformer domain that encodes spatially localized, multi-scale, and orientation sensitive features. Yeah, I'm also not completely sure what that means. The complex steerable pyramid provides such decomposition. Separation local image structure into amplitude, feature strength, and phase, feature position. Okay, so they do this complex steerable pyramid thing and use that on the image to get some other way of representing it or something.
that is a reference from 1991. That is a reference from 1991. That paper that they referenced.
Okay. Yeah, I
feel like a lot to be understood. Yeah,
I mean, I think it's possible we won't be able to understand this paper, but but I mean, it's better. My other option, I was deciding between just picking whatever this or just not doing the reading group. I felt like it was better to just try it. Even if it did look like Gonzalo is right that this probably requires more preparation and having read it beforehand, and maybe read some of the reference to figure out what this is, for example. But let's see what we can figure it out by just looking at it. It also has some pictures, maybe that will help. But let's see first. Okay. So we do not interactively integrate the gradient to trace the full path between classes. We amplified a single local tangent vector. The immediate direction of change in predicted gradient, creating a linear extrapolation that reveals how the model perceives the transition from the source to target class in its feature space. Yeah, this how the model perceives seems like a weird way of explaining things, but okay. These formulations offer new insight into model definition. Like I still don't understand what they are. Like they are clearly doing some kind of thing where you change from some class to another, but I don't really understand what they are doing. I guess maybe they are representing the with the complex pyramid thing. Maybe they are representing the whole space of possible of some data set or all possible images or something. Maybe probably I don't know some data set and doing some kind of thing about where in that transform like in that view of the data set the classes change or something. But yeah, no idea. This information offers new insight to model decision boundaries. Because the steerable parameter represents localized disentangled image structures, rendering this space yield semantically meaningful and especially concurrent transformations. Okay, so they represent this the imagine in this stable pyramid thing, whatever that means, and then do gradients on that, and that means things. Like have some semantic way of representing images and then do grades over that to get some semantic expressions or something. Right. Yeah. Oh, there's also a Fourier transform. That actually is more understandable. Uh, wait, is this terrible pyramid something similar to doing a Fourier transform of the thing? But I thought it had something to do with semantics. I don't know. It's Oh, I see you muted. Were you going to say something? If you're talking, I'm not hearing you right now.
Oh no, I just yeah, they do talk compare like Fourier transform with this pyramid thing later.
Very nice. Uh, did you like? It seems that you already read the paper or something. Did you actually understand it?
I mean, I tried. Like, I didn't read it very in detail. I kind of
Okay.
skimmed over it, but yeah, I mean, I think I kind of see what they're trying to do, but I don't understand because I don't understand the underlying things of whether or not it makes sense, is I think where I am right now.
Okay. I mean, okay. Let's keep going, I guess.
Yeah.
uh, yeah. So they do about yeah they. Yeah, they do this thing that is very novel and whatever. Yeah. Uh, on principle, it's on multiple the following domain. Okay. Uh, yeah, there's a bunch of related work on multi-scale signal processing. So the other thing is a face them the Fourier testable primary representations we generate solutions. Okay, but you Fourier representation of what? Of the images. I guess you can do the Fourier like some 2D Fourier transform of the images, and that might tell you, and if you take gradients over that, maybe that tells you something interesting. And I feel like don't like immediately understand what. But that's closer to make sense, I guess. Okay, method. Maybe they explain it better here. We begin by applying an invertible transformation f to the input images. Okay, to obtain representation in a different domain. Okay, so they just do some transformation. wherever you represent denotes the coordinate in the transform domain. Frequency of position square orientation. Ah. Okay, so they turn the images in this other presentation where you have some other space where you have some coordinates for each image, and they basically find which parts of that space actually correspond to different classes, and that tells them something about about images in general. I think that makes sense. Although I don't, like, at least with Fourier transforms, for a lot of things it's not going to be very meaningful. But okay. Let's see what this is saying. To discover the direction in transformer space that maximally increases the likelihood of the target class T, we define a loss and compute its gradient with respect to the transform domain coefficients. Okay. Yeah, they just do it to Okay. Yeah, so then you do some transformation on the images and then do gradients over it. Okay. The choice of transformation significantly influences interpretability and granularity of classifiers morph visualizations. Okay, whatever this means. A transformation domain is splitting encodes locally structural properties as orientation, scale, and partial positons to support meaningful. Yeah, but the orientation is scale or what? Like if you have numbers of the number. Yeah, I know. In the Fourier domain, phase carries the bulk of perceptual information and encodes positional information with high sensitivity. The phase component is particularly detecting and manipulating the finest scale structural shift and motion information. Yeah, like for more image things, I'm not sure like why you care about phase in the Fourier transform. Like I feel like at least here, like if you're doing this kind of thing, what you still need, like you want to, if you want to get some meaningful explanations of what the model, how the model is deciding between classes for images here, you are basically going to need some representation where you are already classifying the inputs on basis of that. You're representing that semantic meaning on the thing. I guess it's still kind of similar to the other to the typical thing where they are doing for inputs. Maybe some of them do input space, but they usually want to look for some specific thing, like is the model racist or something, and maybe you can represent some transformation that represents, I don't know, the race in the input, and you can see if the gradient. What, I don't know how much I'm inventing a completely different thing versus understanding it, but yeah.
Yeah, I think it very crucially depends on whatever this steerable pyramid thing does. I mean, like their whole argument kind of rests on, like, they say that the choice of F is very crucial, and so they choose F to be this steerable pyramid thing, and Yeah, I mean, like, and they say that this decomposes the, the image space into like interpretable things. Like, one represents the amplitude and the other represents like local features in some sense.
Yeah.
So yeah, I mean, so like their claim very much depends on that, and yeah, I that part I don't really understand.
Yeah, I don't know what the Steerable pyramid is. Wait, let's see the results. Maybe wait this version. But yeah, basically, so maybe you can find something. I feel like the interest there is an interesting idea here of like that. I don't know if the steering primacy is useful, but I think there's an interesting idea here of you're doing the kind of this, what was the name? If you are doing things like saliency maps, there is a slightly more interesting thing you could be doing. Instead of doing that on pixel space, you can do some transformation on the image that has some semantic meaning. Like maybe you just have some score for the images or something. I mean, I guess you will need to have, like, for you think a problem is you need to have some transformation you can take the gradient of. Uh, but yeah, so you have some transformation and you do the gradients in that input space instead of doing the gradients on the pixels, and then you maybe get some interesting things there. You can do this kind of thing. Uh, But the problem is for most problems people care about that are not toy things like this thing, what I'm guessing is just mostly about
Yeah,
where this thing is on the image. Like they were not basically very basic vision things where you care about the position of some simple object on the image or something. Uh, you don't have nice transformations that do this because I will need to check, but I will guess that you need the transformation to be uh, to be something you can do gradient descent on to have the gradients work. And so in the end it seems like maybe you, for example, I mean maybe you could use another neural network for it, but at that point that seems kind of you are trying to use a neural network to understand another neural network or something. I mean, I guess that could be interesting. Like, you take some simple classifier of, some simple features about images that, some more lower level input features, and you have some bigger model that does more abstract stuff, and you use the small model to try to see if the bigger model, or it doesn't have to be a small model, it could be another model, like to see if some classes depend on other classes or something. I'm not sure this idea makes sense, but seems like it could maybe.
right. No, I think like I think broadly, yeah. Like I mean, if we want to, like, basically we're trying to, yeah, like study how I mean, it's like differentiating class with respect to inputs, right? Because we want to see how does the class change if we change the input,
Yeah,
and if we go from pixel space or like like yeah, like a less, I don't know, like a high entropy space to like a more structured space. Maybe if there's like a transformation that exists, which can always map, like, in this case, an image to like a more interpretable format, then maybe, doing that gradient there makes maybe is better, and you can always, and at least in their case, like they can map back to an image and show that, hey, this corresponds to like a, and this is what a real image of my
Yeah,
of this.
I guess the problem is that we don't. The main things we have to map, some image to some more interpretable space is like neural networks.
Right.
Or at least interpretable, at least things that you can run gradient some. The other thing we have is having humans manually label the inputs, but you can run gradients on the humans, so that doesn't work. So yeah, I do think it's interesting the idea of. I think even then maybe you can use. There is some way of using some neural network to interpret other neural network this way. Like you use some neural network to get some classes about, like, you have some neural net that take images and
What if you just put like a sparse autoencoder?
I mean, but
you
the,
just take a separate learning step where you can just map all inputs to like a interpretable space, and then map them back. So you have that f function as a learned
I mean, I
function.
guess if you have something like that that work very well, you can just do that directly on the model and interpret it.
Sure.
But yeah, I don't know. I do feel like maybe there is something here where you have, because you have classes that are made of more simple things. Like you have some like if you have some classifier that classifies things in cats and dogs, and you have some classifier that does, they can even be the same classifier, and you have some classifier that does the kind of thing where you you have some classifier that tells you if some image has I don't know, some animal or ears or whatever. Maybe you can find something where you get some interesting representation of which kind of things, which kinds of sub features the model uses to determine whether something is a cat
Right.
or a dog.
Yeah, let's say you have like a catalog of like I don't know, like 100 such classifiers, and then you somehow use those.
Like you could, I mean, you could have even the same classifier. Like you can apply it to some images to get it interpretable space, which is just has a high number for different classes or not, and uh, you can try to use that to figure out which classes matter, like other. Uh, which features of the input matter for the output. This is especially more interesting if you have something that is not really a classifier, is taking images as inputs, and you could run some, like, I don't know, there is some dumb example I think I saw in some tutorial was something that you give it an image of house, and it gives you an estimation of how much money it might cost, and you could have an image classifier, apply that to the images, run gradients to that, and try to figure out which features the other model. Or, for example, you can have something more realistic and interesting. If you have ChatGPT, you can input images on, and you can ask it questions about the image, and you could do something where you have some image classifier thing that you apply to the input and take grades from that and figure out that way which kind of features of the input the model. But yeah, this all seems like a super hacky thing that I just tried to think of what could possibly this be used for. And the actual thing they are doing here is maybe not that interesting, or maybe if I understood what the pyramid thing is, it
Yeah,
will
the other
seem
issue,
more interesting. But
the other issue, if you go back to like their method, like their basic, their above this. This part, right? Just above the choice of transformation. So they map it to this other space, and then they find like one gradient. They do one gradient computation at like at x, which is like the input position, like whatever the input is, and then they gradient computation from there to to the direction in which the class changes, right? So that's how the loss is. So like you want like to go to like some target class T. What is the direction that I should move in? And then they basically, they don't do any other. I mean, then they do not like reach. I mean, it's almost like it's a linear thing, and then they just like do essentially like a linear interpolation in these steps of alpha, and at each step they generate like what the next thing is, and then they convert it back to like the image space, and then they show the image. And I don't understand why that works. I mean, why would that work? Like it's like taking one gradient, like just you figure out like this is the direction, and then I mean, it just seems, I don't know, like maybe it has to do with the fact that I mean, they say that this is coming from all that motion magnification stuff, like
yeah,
that's the logic, but yeah, it just seems weird.
yeah, that's also, I was ignoring that because I didn't understand the time. I was mostly just thinking about the more general thing of taking gradients of some transformation on the input for doing salience maps kind of things, but on some other space. But yeah, that's the part where they do the interpolation. Yeah, I don't know. And maybe they are just doing essentially doing some linear approximation, and if you don't extrapolate much, it works. But no idea.
Okay.
So what results did you get?
Yeah, one more thing, and maybe you have some thought on this, like that it's not clear to me is, let's say there is some transform, like forget this particular transformation. If there is like some transformation and I do figure out like that in that transform step space, these are the steps to go from like, from input image which is of class A to like something of class B. I mean, how do I know for sure that, that the actual that the neural network also, like the original neural network or the original space uh, also like, works the same way, like has the same structure? Uh, is it just
I
because it's
mean,
invertible? I'm not, yeah, it's just,
there is some transformation, right? Like if you are, mm, so like for the Fourier example, like it is invertible. Like if you take some transformation and I mean, at least on the example with Fourier transformation, like if you find that some phase thing with with the Fourier transform, that some class changes with the phase thing, that should also work on the, like you're just taking some transformation of the image, and it's things that are true for that should be true of the, yeah, I just don't understand the, the thing.
okay. So some sort of like, I don't know, like linearity should be assumed, right? For that to be true. I mean, like you could have transformations which like break that structure on the original space so that something is true for like the original space but no longer true for the other space. And
Yeah, I mean, I'm thinking of like on the on the Fourier transformation, right? For example, the way to think about it seems to me to be that the Fourier transform image means something about it represents something about the original image. Like, I don't know.
Right.
Instead of that, imagine if you have some transformation that tells you how green or red the image is, and maybe then the transformation to just have some coordinates, but the structure, the idea of the transformation is that it represents like how green or red it is. So if you find some that making the image more to the coordinates that represent red makes it have more of the class or whatever, then that just means that red makes the image being red makes the class go off. So it's not like it's not that we are looking for some structure on the transform image that might be or not be on the first one. I'm thinking of this as the transformation represents things, but maybe I'm misunderstanding something.
No, I think, yeah, I think they also say that it has to be invertible, which means, I mean, it cannot be like a super lossy transformation, otherwise you won't be able to invert it. So I think, yeah, that probably puts constraints. Okay.
Does anyone else has something to say about the paper? Because I don't have much else. I guess I don't. I guess I could look at it a bit more, but I don't feel like I'm going to understand it a lot better. It doesn't seem that interesting. I think it's interesting, like the vague idea that if I did something related to that, it would be more inspired by the paper than actually using any of the paper. But the big idea of doing gradients in some transformation of the image that has some meaningful semantic thing, maybe there is something there, but at least to me, the thing on the paper doesn't seem like super interesting or useful by itself. Like if you are doing this kind of, I don't know about the pyramid thing, but at least if you are doing things like Fourier transforms and the pyramid thing is something similar, you are not going to add super interesting semantic explanations out of your thing. And it feels like to get actually interesting semantic explanations, you need some way of already like classifying having some semantic decomposition of the images already. And I think the only way to do that is through neural networks. At least the only way to do that actually works in practice and you can do gradients on. And maybe there is something cool that you can do with using neural networks to classify inputs and then do gradients on the classifications, including the network transformation, to get something like which feature of the input causes some output. And maybe some text version of this could help you find backdoors or something. Like if you have some output of the model that, like, if you could try, you could have some some model classify some text on different kind of texts, like some give it some classification or maybe some scores for different things, and then you take the another model and see when it outputs some harmful response or something. Try to see what features of some input can cause a harmful response or something. But yeah, I don't have much else to say. Like I'll wait a few minutes, and if nobody says anything, I'll just end it here, I guess. Next week, by the way, we'll hopefully have the authors of the other paper, which seems more interesting, and yeah, that will hopefully be better than me just spending an hour looking at a paper and trying to figure it out. But yeah.
Are there any other examples of deep neural network interpretability? Because I feel like this is like one of the cases where they entirely sidestepped transformers and tried interpreting something else.
I mean, there is a lot of things where people try to do something that are not transformers. I mean, people were doing interp things where they in image models since before transformers were a thing. Like, I don't know, there is all these things that salience maps that I think kind of feels like the if you go to Grisola's old posts, a lot of like the idea of mechanistic interpretability was kind of like you can kind of come up with ideas basically meaning we are doing something that is not this kind of salience map thing where you only care about the input and try to do some gradient on it. And instead we care about what internally the model is doing. Yeah, and there is, even that was on the post, if I remember correctly, that was on the old post of circular equalization with when OpenAI like was trying to reverse engineer an old like some image classifier, and they were doing some cool things with that, and they realized that some neurons on it were polysemantic, and then they started with the sparse encoder thing after that. But yeah, it's not like interpretability is just, and there is a lot of other things where people looking at chess models and things like that. But yeah, even I think didn't maybe I misremember, but didn't David Bow do a workshop in some big conference for image model interpretability maybe? But I might misremember that it was for something else. Well, anyway, I see basically nobody's talking anymore. So, and it's almost been an hour and I have other things to do. So I'll just stop the recording. Well, hopefully because it's kind of dying. I guess I'll close it and hope it
Yeah, I think there wasn't a lot to unpack with this one compared to the other ones in the past.
Yeah. I think also the possibility, if I understood it, I could explain it, maybe. But I just pick it randomly earlier because we last minute decided to change the reading group. Because we realized we could get the authors for the other paper. And I just picked this one because Sion has suggested it, and I just I only had a few hours before the reading group because I didn't pick anything earlier. But I think I'm probably going to try to have like a list of papers for next time. Like prepare for like we used to do that. But yeah, I probably should have a list of papers I want to cover to just pick. I also just found the Neil one because I just follow Neil on what's the name of the thing? Anyway. So yeah, I'm not sure. Apart from just being on Twitter and things like that, I'm not sure where to find to find all the new Mech Interp papers. I guess. Hopefully, as more people join the server will become a better place to figure that thing out. But yeah.